Today I'll be talking about the spatial data analysis components which is available in GIS. So what will I do is that I'll be covering few of the components which is present in different spatial data analysis software tools. So especially like what is the meaning of doing, or what is the how we can use different tools which is available to solve particular problems. So we'll take few problems related to that. So that's what the list of topics which you're going to cover, like why we really need to do a spatial analysis, what exactly the GIS plays roles in spatial analysis tools, what are kind of different queries which is available in GIS, and I'll be going slightly more in detail in various type of spatial analysis tools. Along with that, from the technical side, to solve any problems, what are the different operations or functions which is available in the toolbox of spatial analysis. So it starts from few of the operators like logical or arithmetic operators. These are especially in spatial domains. Then retrieval of few informations, generation of the new informations. That's also will take care. We'll see that how the few of the measurements which being carried out. In some cases, we need to do a summarization of geospatial data sets. So we need to do some kind of reclassifications of the data sets. We'll go specifically in one and two functions related to vector and raster based functions. We'll also have a look of the different neighborhood analysis. This is actually one of the important component, because geography or geospatial analysis is actually works on a principle that all the related features are actually co-located. So it works on that principle, especially in the spatial domain. So neighborhood analysis plays an important role. And we'll also see the few classifications of local, zonal, and focal operations related to raster data sets, and a few of the steps which is required to carry out a few projects, and especially in the spatial analysis. That's what we'd like to discuss over here. So let's take a problem that somebody has given a problem that we need to construct a high school in a city. And as a decision makers, he may give you a few of the requirements. So those requirements are listed in this case, like the distance of the school should be at least 1.5 kilometers from the existing schools. So that's the requirement. Second one is that the school has to have slightly away from the road, but it should not be completely disconnected from the road. So considering that the 500 meters, so school has to have a distance of 500 and 1,000 meters from the main roads. There's also an conditions that it should not be inside any forest, or it should be away from the normal business areas. There's also an additional requirement which has been put it in terms of catchments. So it's like what we are looking for is that we are basically planning to have a school where the citizens or the school kids are available, so that the maximum kids can join to that school. So considering these four different criteria, we need to suggest what are the different location on which we can create in school. So if you take this problems statement, then there are a few of the data sets which is required to solve this, especially like in the first case, when you say that we need to have a distance of 1.5 kilometer from the existing school. So it means we need to have a layer or a data sets related to different spatial buildings. Along with that, we also need to have a road networks. So that is again a line feature class. Then also there's a requirements to have that it should not be in, or basically the area should not be used for business purposes or the forest. So it should not be marked as a commercial area or as well as the forest area. So accordingly, we need to have few polygons or the land use polygons related to that. And there's additional census data set is required. So the attributes of the different polygons or subsectors within a city also is required. So when all these data sets are being given to a GIS analyst, then he or she needs to solve the problems given over here. So to solve these problems, what all the exercises which we carry out in GIS, we'll see in two ways. Like one is, we call it a vector analysis. It's basically works for all the different vector data sets. So what we need to do is, we'll be using the tools like proximity or buffer tool. We'll be using an overlay union function. So these actually helps in finding out like proximity tools are basic, especially the buffer analysis will help us to find out the range. In the previous case, we have seen that there is a requirements to have a 1.5 kilometer buffer of distance around existing school. So considering that, we need to create a spatial buffer of 1.5 kilometers around those schools. We also need to remove or and basically all those area which is even though away from 1.5 kilometers, but they are actually falling in land use of business area, or maybe the land use is actually a forest type. So we have to remove those areas. So for that, we need to have an overlay or union operations which will be carrying on. There's an also a need for finding out the distances from the existing road. So that's what we're talking about, is that we need to have a distance of 500 to 1 kilometer buffer. So that's, we call it multi-buffer analysis tools, which is being used in a vector analysis under the vector analysis group. And then we remove all those area which are not required. So it means like the area which is not fulfilling any of those conditions. So for that, we use clip, overlay, and erase functions. And finally, we need to have basically the demographic data, especially related to citizen age between 15 to 19 years old, so that we can club all them together and then try to find out whatever the distance-based approach is being followed, and after that, the data, whatever is being left, then we are going to do an intersections to get the data sets. So basically, the total analysis, what it does is it tries to find out a list of functions related to in a spatial domains, especially in the land use data sets, related to demographic data sets, related to existing classes, existing land use data sets. So combining all those in a step-by-step manners, we can solve the problems which is being stated earlier. Now let's take the another problems. This is specifically taken for the data sets where we are going to have a data in raster formats. So in this case, what is being asked is that if somebody wants to build a new house, so he or she may have few criteria. So in that case, how the GIS analysis, especially in the raster analysis, can be used, we'll just have a look of those. So over here, the conditions is being laid out like the area should be within the city boundaries. So it should not be outside the city boundary. So there has to have a city boundary extent, or maybe the municipal extent, which has to be there. Along with that, we need to have basically locations where the slope and distances should, the slope should not be at a particular height. So we need to have a particular slopes. So for that, the relative locations and distances from a specific area is being fixed, also fixed. Then also the other requirements are like the data sets or the locations should be currently should not be in the built up area. So it has, because in the built up area, the cost of land will be more. So accordingly, we need to have a place where the built up area hasn't come yet. So that's the requirement has been put. It should also be away from the cemetery, or it should not be any natural areas, like it should not be any uh, forest or any water bodies around that. And then we need to also have a distance based or the proximity based requirement related to that. It should be at least more than 500 meters from the main road. So in that case, what we are having is we are looking for land use classes, especially the feature class, the height or raster data sets, which will be having, and as well as the main roads, especially to find out the proximities. So under that, what we do is in raster analysis tools, we generally do kind of steps like conversion from feature to rasters, because all the operations which we are going to do in the raster base, and few of the specific softwares which works only on raster based data set itself. For example, Ilvis is the one of the GIS tools. Even though the data set will be given in vector format, in Ilvis, all the vector data has to be converted into a raster format, and then the analysis will be carried out. So to solve those problems in a raster-based analysis, we need to do a conversion from basically the feature class or the vector data to raster data sets. Then we need to do a classification. So generally there will be a multiple classes of land use. So we need to look for land use which are suitable and non-suitable. So accordingly, we need to classify them into. So for that, we'll be use reclassifications techniques. Then there is also a specific height layers which gives the layers in a suitable or not suitable. So that's again we categorize in a different groups. It's basically grouping the data sets into two different sections. Then what we do is we create a distance from the main road. So that is being carried out in a Euclidean distance-based approach, and where we can decide what is the grid cells, and based on the distance raster matrix is being created. Along with that, we do after creating that distance matrix, we do a classifications as per the requirement that the area has to have should be away from roads by 500 meters. So that criteria has been taken that any distance which is less than 500 meters is not suitable. And then after creating all these different suitability maps, what we can do is we can do a simple arithmetic operations to create final data sets. And that final data sets will give you a kind of solutions, especially in numbers. That again, we can do a classification that the areas which is where all the three different conditions are being fulfilled, none of those fulfilled, or at least two conditions got fulfilled, and that way. And finally, when we do a visualization of those results, we can make choices based on any other additional criteria. So these two problems basically talks that in spatial analysis, we have two different set of toolbox. One is related to a raster-based approach, another one is the vector-based approach. So in both the cases, depending upon the problems and the software limitations, we have to use appropriately to get the result. So after seeing those two problems, we'll just go in and try to find out that if those problems is being given, what exactly in the functionality which is being provided by different spatial analysis or data analysis tools. So before starting that toolbox or the list of toolbox, let's first see what exactly is the meaning of spatial analysis. So spatial analysis generally in GIS is required to build capabilities within the softwares so that any spatial or non-spatial data sets which can be used to solve especially the problems related to spatial relevance. And they are also being used to identify the different process and patterns which is produced in a space. And they helps in like identifying different patterns, identifying and understanding the different processes. The few of these processes can be like if somebody wants to study why a particular city is growing in a specific way, because in GIS, generally in the technical areas, what we see is like any rules and law is actually fixed and it's universally applicable in all the areas. But in GIS, it's like in each of the cases has to be considered specially. For example, if question is that why that particular city is growing in northwest sections, or why the particular city is growing in circular fashions, why there is an elongations in a particular direction. So if we want to find out such kind of spatial analysis, then the patterns and process needs to be understood specifically in a context. And based on that, the different pattern identifications and the understanding of the processes needs to be carried out, which is actually a spatial analysis tools helps in doing that. So in GIS, especially the first sections or the portion, GIS, actually spatial analysis has again multiple areas. One is specifically tools related to which is available in under the GIS toolbox. Few of them are actually a part of the kernel density functions, which comes in extension of different kernel-based processing systems, which is at and it's being considered as a higher level tools. And then there's also a tools which works in uniformly across globally in whole study area, or there may be cases where the tools has to take the local variability into consideration. So we'll just see a few of the GIS capabilities or the tools which is available. So GIS has, as we have we already know that it basically deals with the geographical reference data sets. It will have a few spatial attributes and capabilities. It allows you to do some kind of conversion functions, like in raster analysis, we need to have a data set conversion from vector to raster. So those conversion tools are there. There's also requirements to do an organizations of spatial data sets and attribute data sets. So any polygons, line, or point, or features, if you want to have an attribute data associated with that, so we need to have a capability to link them, so that the GIS also have a way to organize those data sets. It also allows you to do manipulation of spatial and attribute data sets. Those manipulations tools are actually helps in solving and understanding the problems in hand, and then it also lets you to find out the reasoning of any specific processes. And finally, we need to have a capability to communicate back the whatever analysis we do, so it should have a kind of presentation and display capabilities. And in spatial analysis tools specifically, it has many different combinations. A few of them are actually being put it as a default tool sets, which is available in any of the GIS software. For example, the buffer analysis tools, it is going to be present in any data sets. So you go for a commercial open source software, you'll have all those data sets or the functionality present. But few of the tools are actually in a software specifically written for as a module, and those works only on those specific software. So let's say that we are having a data sets which is being prepared in GIS environment. So this just shows our different districts in a specific locations. Like in India, we are having a different district. So all the district maps is being put in over here. And then we need to do a kind of analysis for maybe at a city level, or maybe at a state level, or there may be a cases where we want to work on in the city itself, so city and ward level itself. So there are different variety of scales which is possible, and each of those the spatial data sets needs to have an attribute associated with that. So accordingly, we'll have a few attribute tables which will be present. Now we'll see in a spatial analysis tools how we actually use those attribute and spatial data sets to achieve different spatial requirements. So generally, in spatial analysis in GIS tools, we generally carry out, or we say the classification is being done in three different categories, like attribute query, spatial query, and in some of the cases, we generate an additional information. So generation of the new data set is also possible. Attribute queries and spatial query, actually these are going to work on specific data sets, and they doesn't create any new data sets, rather than it works as a filter. So you may be having a lot of larger data sets and we want to create a subset. So under the creation of subset, we carry out attribute based query and spatial query. But in case of generation of the new data set is there, then there are tools like buffer, proximity, kernel density functions, kriging. So these are actually helps in to finding out the new data sets which gets generated. Let's take a few example of spatial analysis, like raster-based spatial analysis. If I take, then the reclassification is one of the requirements to have raster-based spatial analysis. And there's an also these reclassification are required especially for the I should say the aggregations or the summarization of your data set. For example, if I say that you may be having a raster data set in a DEM format of a particular area. So in a particular area, you may be having a height variations from, let's say, 600 meters to 1800 meters. Now, if you want to do a categorizations, then what we do is we do a classification based on basically on the basis of heights. Like we can create a 600 to 800 is one category, 800 to 600 another criteria, and so on. That is actually required because whenever as a human being we want to do a data simulations, we need to have classes, maximum 7 to 8 classes, that's easy to comprehend. Otherwise, it becomes difficult to do analysis. So for that, we need to have a reclassifications tools. We also need to have a spatial queries toolbox, which allows you to do or carry out the activities, especially doing on a spatial domain. So let's see a few of those tools and classifications. But before going into that, we need to see that how the different spatial operator works. So it's like the way the set theory works. Similarly, in the spatial domain also, the different polygons can interact and the corresponding operations has been created. Like if two conditions needs to be fulfilled in two different feature classes, then the intersections can be used for finding out the common area or spatial areas. If the two different conditions are there, let's take an example that we have found out all those areas which is away from existing schools by 1.5 kilometers, and we have also found out the another conditions that the areas which are actually away from the road by 500 meters. So there may be cases in our problem statement, we need to have an AND operations because both the condition has to be fulfilled. In some cases, there may be cases that these two conditions may be an optional one. So any one of those conditions are there, we can use union operations. We can also use the exclusive XOR operations and not. So these are actually a set theory based operations which is possible in a spatial domain. There are also an arithmetic and relational operators and as well as trigonometric functions. So these are actually required to do a modeling purposes. Like if somebody wants to do an head logical modeling or to find out how the different water flow is actually getting affected with the soil types, and the corresponding different coefficients associated with that. So for that, we do require a few of the mathematical tools to do a complete modeling or simulation area. So for that, the relational and arithmetic operations are also being provided. But how does the spatial analysis tools makes, or it looks different from the list of operations which I've seen earlier? Because in the logical arithmetical tools is, or the operations are actually is being used in any domain of engineering. The most important aspect in spatial analysis which we work is the topological relationship. This basically talks about the topological relationship are actually tells that how one particular feature is actually related to another feature in a spatial domains. So, and those kind of requirement is there. For example, if somebody wants to have an road widening requirements are there, and in those cases, if road widening needs to be done at only on the left side of the road, not on the right side of the road. So in that case, we need to have a kind of understanding what exactly is the meaning of left, what exactly is the meaning of right. So that kind of semantic, if you want to build it in our data sets, then the topological relationship actually helps in doing that. So it needs to have, and based on that relationship, we can define different operations between the features, especially in the spatial domain. Like if you have a conditions that is one feature or is one feature is not related to the other features. So those may be area like, for example, if you want to do an urban planning, then you would like to have a new area which should be away from existing reserve forest and so on. So it means like those two areas has to have a distance and they should not share any specific boundaries. So that kind of operation, if it requirement is there, then disjoint is actually operations which can be used. In some cases, we need to have a specific operations like meet, which actually talks about the connectivity or contiguity of two different locations or two different features. So is it possible to have a continuous connectivity? So that is basically is being can be, the meet can help in doing that. We want to do an equivalence test. Let's say an example that is the Indian boundary is covering all the boundaries which is being generated from the state boundaries. So in that cases, the equal operations can be used. We need to find, and so similarly, we are having a different topological relationship like inside or covered by, the contains and covers and overlay. So these operations are actually, these 8 different operations are actually based on the topological relationship of different features. And all these topological relationship which we are talking about currently is actually in 2D domain. So it means like we are talking about the planimetric representation of the data sets, and based on this topological relationship are created. We are also having a topological relationship in 3D domain, but we are now restricting to only in planimetric domains for finding out different topological relationship. To see the few of the spatial operations like union operations. So let's say that we are having two features which is being shown over here. Is one is the blue color, another one is the yellow one. So if you do an union operations, then the total area actually will be which will be covered by both the features. So those areas are included, and that is actually an output. This actually may look quite simple, especially in spatial domains, but there also needs to have an attribute mapping of all the features present in input layers and to the corresponding output layers. So the mapping of the data sets, wherever these two data sets is having a common area, will have both the attributes available. Where in cases it is in case of the area which is not being covered by one features will have another feature as a null value. So that's the actually output in attribute operations will take in the union. The click operations are actually if you are having an input features and you carry out or you have been given input areas, Based on that, you need to extract the information. So that's what we do it with the clip tools. And that clip tool is actually can be used to extract the area. This is basically being used in the cases where we have to have the boundary, or based on your study area, you want to bound your study area. So so you're having a specific study area. Now you may be having a large number of data available. So we want to restrict our analysis within a study domain, so that on those cases we can use a clip features to extract the informations of different layers, and then we carry out the analysis. Then there's also a tool like erase and intersect. So the way the union operations works, similarly the intersect also works. Only difference is that it only gives you the information which is common in both the layers, especially in the spatial domain. Where the erase actually helps you to create a hole within in your area or input data sets, where we extract the informations, and then whatever is being left is actually an output. So the clip is the erase is actually just a complement of the clip functions, if we see in that way. The dissolve functions basically helps in aggregations of data sets in a spatial domain. So let's take an example that there may be a multiple classes of forest. For example, you may be having a forest area of pine forest, needle forests, something of that categories. There may also be in urban areas can be having a multiple classes. For example, you may have the commercial area, residential area, semi-urban areas, and so on. In some cases, what we need to have an aggregation of these. So we'll say simply a residential area and forest area. So in such cases, we can use the dissolve tools to merge the different subclasses which is present in your input data sets to create an coarser level aggregated functions in the spatial domain. So that's the dissolve operations actually works for that. And buffer analysis tools is the most common and widely used analysis tools. It basically helps us to create a designated area around a specific feature. So in this case, we are seeing a line. Along the line, what we are doing is that we are creating a zone. So those zones can be a single layer given based on the input layer. So that's also, we call it that we need to provide an input from a specific locations. And there may be a few buffer analysis where we create a multi-ring buffer. So multi-ring buffers are actually the distance of buffer which we create it at different layers. So for every 500, 1.5 kilometers, 1,000 meters, or 1,500 meters, that way. So that way the multi-layer buffers can be created. So these tools are actually is specifically applicable to in case of vector based data sets. So we'll see the attribute which is being generated from these data sets in each of these operations, how the spatial data sets are being created, and then correspondingly how the attribute gets transferred from one data sets to the other data sets. So we are having one input and the corresponding two features are there. So based on those two features, if you see in the intersection areas on the spatial domain, whatever is the common area that will be taken in. And in each of these sub area which is being generated in output locations, the query is being fired to find out that is the data is present, what is the actually attribute data which is present for in an input feature, and what is the input layer 1 and input layer 2, and the correspondingly each of those sub areas within your output is actually gets filled up using the intersection tool. So that's how it's being shown over here, that each of those 8 sections is actually having an output from based on input and output layer. One important thing which we need to see in intersection section is that each of the input feature which will have a different extent of a map, finally the output, whatever is will be generated, will be actually the extent of your map which is common in both the areas. So that's the extent operation has to be carried out in the cases. In the extract cases, we simply use the tools based on that the output is getting, or the attribute data gets generated. Again, we see over here is that the feature by which the clipping is being done, the output data set will actually have the input data set's attributes. So if the input data set is actually having over here is the B1, B2, B3, and B4, these four attributes actually gets transferred from input to output. The attributes of the clip by features, which is A1 and A2, is actually not getting reflected in your output result. And over here, the clip by feature only works in a way that it does only the extent which is being present over here, restricts your boundary extent within that range. So there may be, the way we are having a different tools for the vector data sets, we'll also have an overlay operation which is possible in raster data sets. In the raster data sets, what we do is we calculate or generate a new values based on performing operations on cell by cell basis. So it's like on the each grid, a computation is being carried out based on the criteria, and then the output gets generated. So in other way we can say is that in this case actually the no geometrical calculation is required. We just need to traverse the whole grid, and each of those grids which we are assuming it to have a similar projection and extent. It means like one of the grid can exactly sit on the top of other grid. So if that kind of conditions are being met, then we can simply perform the cell by cell operations, and those cell by cell operations will be actually a function of different arithmetic or logical operations, which is actually a raster calculus operation, which is also called. So that output will be generated on that. So these raster-based operations again are very, it starts from the very primitive operations like arithmetic operations, or in cases of carrying out the arithmetic operations. So let's take an example that you're having a two features A and B, and in one case we just want to do an offsetting of the data sets by a particular values. So those offsetting we can do is to create a new data set. So that is being the first condition is being given. So in this case actually the single data set input is there, and by the constant values the offset is being created. In case of the multi raster analysis, what we can do is we can take different data sets, combine them together. So in this case simple arithmetic operation is being carried out, like addition of those the values, those two layers, and then we can create an output. We can also use different mathematical functions. We can have our own customized functions to put in our the cases, like in the C3 condition, or the C3 operations are actually the cases where which looks like very similar to the NDVI generation. So you may be having a layer of A as an red band and B as a IR band, and based on that we can create the NDVI values as an output. The comparison operator. So in the earlier we have seen that there was a problem of finding out or creating a new suitable houses. So based on different conditions we created outcomes as a suitable, non-suitable. So for each of those conditions in a spatial or grid-based approach, we create multiple conditions. And based on that conditions, what we can do is we can apply a list of operations and then combine them together to generate an output. So if you're interested that all the three criteria has to be fulfilled, then we can directly use AND operations, where if you want to say that any one of those two condition is sufficient, and then in those cases that all the conditions, all the places where the two different conditions are fulfilled can also be used to generate the outputs. So in most of the cases, the output layer are simply an operation of the two different raster layers, and those and like in this case, like the output raster layer may be generation or the wherever the first suitability is not matching with the second suitability. So that kind of conditions which we can create it for XOR operations. The overlaying function, so that was the cases where which we saw the different raster based analysis where the overlay the simple mathematical functions has been used. Now over here we'll see that there are two different layers are there, and each of those layers are actually two different conditions is being taken in, and the final output generation is being created. So like you're having a forest area of type A, and the other one is the height-based criteria. So considering these two, if the condition is getting fulfilled either in terms of AND or XOR operations, the corresponding outputs can be generated. So we are also having the output ways where we can do a conditional-based raster spatial analysis, where we can put if any condition is being fulfilled and that is suitable. So it's like this is basically useful to creating a suitability-based maps, where we can say, yeah, if this condition are fulfilled, then those are suitable, otherwise not suitable. So that kind of conditions can be used. Okay. So the other way of finding out the overlay operations are using the decision tables. So what we do is we take two different decision input tables, and based on that we combine them together to find out what exactly is the areas taking two different condition values, and that gets generated. So it is basically being used for suitability analysis to find out the operations, and based on that the suitability and non-suitable conditions can be fulfilled. So this is just showing an example where land use and as well as the geological components of analysis is being used to generate a suitability case of an area. So depending upon the soil type and the corresponding land use of forest, grass, or lake, we can find out the area which is basically suitable or non-suitable. Coming back to the spatial selection queries, these are actually also called an interactive queries. So in this case, user actually gives the input, and based on those inputs, the events, the different operation gets triggered, and the correspondingly the output gets generated. So either the spatial selections can be done based on the attribute conditions, where we can use different relational logical operators, or in combination of those operators, or we can also do an interactive query based on the topological relationship. So how one feature is actually related to the other features, especially in the spatial context, we can carry out the queries. So it's basically finding out all the area which is on the left side or right side. So we'll see a few of those examples in this case. So this is the case where we are having interactive queries. So we are having an attribute data set which is present in a tables, and corresponding the output data sets are also present. So what we are doing over here is, especially as a user, he or she will select a specific row which correspond, and then each row is actually corresponds to a attribute data of each polygon. So as soon as any specific row or attribute is getting selected, the correspondingly on the visual display area, the spatial features will also get reflected. So this is actually a attribute-based query where direct interactions is being done on the attribute tables. There may be a cases where we would like to have a multiple features selected. So what we can do is in a spatial domain. So first, in the first case, what is happening is that we are doing query on attribute data, and correspondingly we are trying to see what exactly is the output on a spatial domain. There may be also cases in the spatial domain we want to do a query, and then finally we want to see what are exactly is the values. So in the first cases, let's say for example at a specific district, what are the neighboring districts connected to a specific district. So in such cases, we can find out, select those area which is neighboring to a specific districts, and then we can do a query on finding out what exactly is the data sets around those areas. So we can find out the actual attribute based on. So these are actually called interactive queries because the user needs to do an interaction either on attribute tables or on the spatial domain. So in any of those cases, the user interaction through input methods like keyboard and the mouse is required in this case. There are also on conditional, especially on the attribute-based query. So what is being done over here is that we put few conditions in your query language. So these queries are very similar to the SQL languages which is being used in databases systems. So in those cases, actually we put few conditions, and based on that we can find out and we can do a queries. But only difference over here is that in the normal database management systems, we have a query directly on a tables, columns giving you and putting some conditions. But in case of spatial databases, what we can have is that the spatial functions can also be used in. For example, maybe we may be having a data sets in our spatial data sets giving each point locations and corresponding attribute. Now there may be questions that find out all the points which is around a specific point. So in this case, actually a distance-based function has to be built in as a part of spatial functions within a database. So that's the actually spatial database systems will be needs to spatial database management system has to have those spatial function built in as a part of any query analysis, and it also needs to be in alignment with normal SQL languages which we use. This is just an example where we can do a query. So we can just give them where conditions of area, conditions, and all those areas will get highlighted. These are actually useful in finding out any suitable area of or the prescriptive modeling process where we try to find out what exactly is the areas fulfilling all those specific requirements. Then the conditions can be as the logical and operations are there, so we can have a different attribute based conditions, and then those attributes based conditions can be combined together with logical operators like and, or, and not. So this is actually an impact of the output. In the first case, we had a very large number of polygons where after the analysis or the putting the second condition, it got filtered it out. So accordingly, we can combine multiple conditions to generate the output. In case of proximity-based query, what we can do is that we can have a list of polygons, and within the polygons which we need to find out the other points. And this is actually the area where the spatial analysis actually deviates or branches out from the normal SQL query analysis. So over here, what is happening is actually the distance-based functions, containment functions, those are actually is being built in as a part of query. And with the help of that, the analysis or the functional and the algorithms, the output gets generated. Because and or logical operations are actually available as a part of normal SQL queries, but in such cases, like inside a particular polygon, any other points are there, or is all those points which are away from or outside those polygons. So these kind of conditional, the spatial condition-based functions actually works different, and these are actually a new actually extension of existing database management system. So generally we'll have all the points. In this case, we are seeing two different cases where attribute is getting selected based on all the spatial features, and based on that we are seeing the cities around a specific word. So we are seeing that conditions. We can also see the cases where one particular feature is interacting or intersecting with the other features. So we are having a road layer, we are also having a polygon layer, and then we want to find out like all those road networks which is actually interacting, or is it going through a particular polygon. So that is also being shown in this case in intersection functions which works. This is actually an adjacency based matrix is being built. It's also called the it's actually being used to find out the connectivity and cost associated with around a polygon. So what happens is that in some cases we need to have a find out failure of specific points. In such cases, the adjacency matrix is being used. So taken any polygons and you try to find out what are the other polygons which is at a distance of, let's say, first as a neighbor, first neighbor, or the second neighbor, or the third neighbor. So in mathematics, it's called as first order, second order, and third order, and so on. So any first order neighbors is being shown over here is that in a specific state over here, like Georgia, which we want to see it like what are the other states which is adjacent to it. So these are actually first order neighbors which is present for state Georgia. And then we can also find out the second order and third order neighbors. So this is actually a distance of 2 and 3 neighbors that can be completed. But to find out such kind of adjacency of features, we need to have specifically the topological built-in data sets. Actually, in the GIS domain, most of the time what happens is that we create data sets, but the topological relationship are not being taken care of. And while creation of the data sets, we needs to be very careful whenever we create any data sets. Earlier, actually there was no support for direct support for the data sets. So people have to have a topological consistency and needs to be built at a later stage. But nowadays, all the GIS software allows you to have a topological editing within a software itself. Like if I talk about the ArcGIS, it allows you to have a specific tolerance. Within that tolerance, if any new points is being created, so two different points will get merged and will have a contiguity of features. So that kind of the topological based editing has to be carried out. If the data set is not having a proper topological built-in, then the adjacency based analysis will fail most of the time. So visually it may look like that two polygons are actually adjacent, but if you zoom it at a specific scale, we'll see that the few of the edges are actually not exactly overlapping. So in such cases, the adjacency for any feature which is having an where we need to have an adjacency and we need to have an adjacency queries, the topological data set or the topological relationship is a must of those cases. So take the other features which we are seeing is that the buffer based analysis. So in one case of the buffer analysis is that simply on the spatial domain, you radially go along all the directions. So though in such cases we get a distance based output. But in some time, what may happen is that we also need to find out or get a list of the features which are actually falling within a range. So that kind of cases is possible to get in case of in this case, like all the cities which is at 100 miles from Atlanta is being shown in this case. So any cities which is at a distance of 100 meters is being shown, 100 miles is being shown in over here. So similarly, these are actually is an just an starting of the spatial analysis, where we just try to find out the attributes or the different features around a specific features. But later on, there are also analyses like point pattern analysis, which actually tries to find out what exactly is the relationship. Is there any variabilities are there? So in those cases, actually, let's take an example like instead of having these cities, we may be having an conductivity measured of soil at these different locations. Now we need to generate how the actually conductivity is changing in the whole study area. And that's actually one of the parameters for finding out and doing, and is actually an important criteria in geological applications. So in that cases, we need to do an interpolations, try to find out and generate a new data sets. In those cases, the kernel density functions can be used. And that also, the initiation of that process is actually the query is like this, which is that we need to decide a impact radius of a 1 point. So over here is the way we are having 100 miles. Similarly, we can define what may be the impact radius of 1 point, and based on that, we can create the relationship between different points to generate an output. There may be cases where, so in the earlier case, what we saw is that we are having a single features, and based on that, we are trying to do a sub filtering or trying to put some condition, and based on that, we are trying to generate the output. And in this case, actually, currently what we are seeing is that how we can combine not only the spatial but as well as the attribute conditions to generate an output. So this is just an example where select all the hospitals from a building layer. So it means like we are having a multiple layers of features present. Now we are doing a simply attribute query of type hospitals, and that is getting selected. Based on that, again, we need to find out the basically the distances. These are actually these distances actually can be simple one as based on the road distance, or it may be a cost-based method. For example, what is actually the travel time it takes to reach to those hospitals. So these are actually, these kind of queries helps in service area analysis, where we say that any service points are there, and how those points are actually can be serviced from a specific locations within a time or a point. And based on that, again, combining those two together, we can generate an output to do a combination of these two. So there are also measurement operations for carrying out the activities, especially on the point, line, features on vector data sets. And these are actually a simple calculations based on the measurement of each of those features. We can find it out. And as well as on the raster analysis, we can also do some other activities. So let's take an example that what kind of measurement which we can do it in a points, the measure locations, which is measure based tools which is present in your data sets. So any shape files will have the location built in as a part of it. So what will happen is that if you want to find out what exactly is the location in X and Y coordinate systems, so the GIS tools, the measuring tools will allow you to find out exact location of those points which is being marked. And those pair, actually those will be actually as a pair coordinates. There may be a cases where the locations also may be the cases where it may not be a point but rather than a line. So in case of line, we need to have a list of points which actually is part of any lines. So those lines actually can be, we can find out all the nodes present in a specific lines. That's also possible. We can also find out the centroid of a specific geometry or polygons. Centroid actually becomes an important part, especially for the labeling purposes. Like whenever we want to put a new label around polygons, because annotation is actually again one of the important activity which is required to show what exactly is the output is being generated. So in such cases, the centroid is the actual location which is being used by default to put different annotations of those polygons, like what is the name of those buildings and so on. So in such cases, the centroid is also being found out. In some cases, we need to do an analysis of different polygons and how those polygons are actually affecting a specific area. Again, in those cases, the polygon centroid is being considered as a point location where that the polygon is present, and again the measure or the measurement is being carried out. So the other ways of doing any vector analysis, like finding out the area or a length of a line or a polygons, that's possible, and in most of the software actually allows you to do that. There's in case of raster based analysis, generally those are not actually specific feature based, but the area is actually is being computed based on the raster or the grid size. So taking area or a grid size as a component, as a part of it, we can use the pixel size, and then based on that we can estimate the total area of a specific locations. In case of distances also, there are different kind of distances which can be computed, like Euclidean distance, directly taking an centroid of one grid and taking a centroid of another grid and doing an Euclidean distance. There may be another distances like Manhattan distance and so on. There may be a distances based on connectivities, because in the network analysis or the road network analysis, the Euclidean distance are not the correct approach. So if you're looking for an accuracy, we need to have distances like road-based distance or the feature-based distance to be computed. So that's actually can be carried out in measurements. So basically in any of the cases or measurement cases, what we do is the simple length areas. The area perimeters can also be computed, and then we can also have a density-based approach. So this actually density-based approach is just an initiation of the point pattern analysis or a spatial geostatistical analysis. So the geostatistical analysis, under that actually we first starts with the basic measurements to find out what exactly is the density of each of those points, and that can also be combined together. So in any one of these measurements, the topological topology is playing an important role to determine what exactly is the length. In case of the length, we need to find out the each of those connected points, and based on that we need to find out the distances and combine together to give the output result. So there is in raster cases or in vector cases, we need to do a reclassifications. So generally under the reclassification scheme, what we do is there may be existing data sets, and those based on those data sets, we need to group it into multiple groups. So in that cases, the reclassification is required. Sometimes we need to do an reduction of the data sets to reduce the redundancies and to summarize the data set. So that exactly we do it in reclassifications techniques of the reclassifications of the data sets. There may be cases where the output result, which we can use it as our own tables, as a user-driven tables to reclassify data sets. So there are multiple different uses of those reclassification procedures. So let's take an example where the reclassification is required for finding out the soil-based classifications, or doing a suitability of soils, telling that is it actually an good for agriculture or it's not good for agriculture. The another example is, especially in from the retail point of view, that we need to have an different income group classifications within a catchment area, so that the investments can be brought in, and then the corresponding prospect of the income can also be put in. So in that cases, the income classification is required. So there may be we may be having a multiple survey data sets where we may be having 1,000 different peoples who have been surveyed, and each of their socioeconomic condition is being listed in a table. But later on, whenever we want to combine that with the other data sets, then we need to have a summary of those, and those summarizations are actually is being done with different techniques. The simplistic one is that we can have a simple classifications where we can give income group broken down into equal intervals. So let's say 1 to 2,000, 2,000 to 3,000, and so on. So that way, one classification can be there. There may be another different classification, like the histogram of those data sets can be created, and based on that, we can create what is the first quartile, second quartile, and so on. So that way, we can also do a grouping. So the grouping of any data sets can requires reclassification procedures and then output of this actually gets integrated in your processing, the further processing systems. So let's take a few of the example, and then we'll go for a break. So what actually exactly happens is, like in case of classification and reclassification, let's say you're already having a set of data sets, and due to changes in a rule, the data sets needs to be reclassified. So based on the input data sets, on an average income values, so one classification is being was earlier. Now we need to put it in new classification. In this case, the base data itself gets changed. So based on that, the new classification results gets created. So this is actually a grouping of data based on your conditions or the class interval modifications. There may be cases where the user may have their own tables. So like in some time, what may happen is that you may have a detailed level of classifications. For example, in urban studies, we may be having different areas like plant, residential area, industrial, commercial. So these are actually different land use which is possible in different urban planning. But these are actually very fine level of classifications. What we can have is, again, at the aggregation of these group togethers, and we can have a new set of classification scheme. So in such cases, the user is going to have a table of classifications using which the classifications can be generated. So user need to provide an input types, what exactly was the earlier classifications and what is the new classifications table. So this is actually a classification based on classifications tables. In that case, as you can see that we are having different values present, and the correspondingly the new values, the aggregated values is getting generated. So finally, at a range of different values, which is present over here of different elevations, are actually getting converted into 5 different categories, and those categories are actually is getting the new summary data sets gets created over here. So earlier, whatever the float data set was there, that got converted into integers, and those integer values can be considered as a representation of each of those class. We can also have exclusion of the few of the features in a group. So in this case, like any elevation values between up to 1,000 meters will not be always not suitable. So that kind of conditions can be put in, and that's how the area is actually looking black in the output map. Okay, so in nutshell, actually what we can see is that in spatial analysis, basically we go for the neighborhood characteristics, and we perform a lot of location-based interest or spatially extent-based approach to find out the neighborhood functions, and we also find out what exactly is the target. Okay, so we are now resuming it to the topic of spatial analysis. So now we are going for a neighborhood functions uh, analysis, especially in the that's actually tools to be used in a raster cases, and how it's slightly different from buffer analysis. Now it's a part of extension of the buffer analysis, but we'll see how this is being used in different cases. And then we'll also see in this session few of the advanced GIS applications which is being used in a different problems, and how GIS can help in creating those problems, especially in 3D GIS and corresponding geovisualization components, and different characteristics of the pattern identifications, and how that can be used to create or do a simulations. So before going to that, let's finish this spatial analysis tool, specifically the neighborhood functions. So under the neighborhood functions, generally any guiding principle for geospatial analysis, or first analysis which started, is actually based on the vicinity base. What happens is that in geography, it's being always been a law that any processes which are interrelated will always be a co-location. So there will be a co-located at a specific areas if there is influence of one process on the another one. So in such cases, the vicinities plays an important role. So it's basically a way to find out different target locations from within a spatial extent. It also helps in determining the neighborhood cases, and then also it helps us to characterize the computation of or the computations of each of those neighborhood values. So let's say that we wants to find out a medical shop which needs to be put in, and to find out, and we also needs to give distances, or in term of the distance cost associated with that. So we want to say that a particular medical clinic, what is actually a service area of that clinic. So to compute that, the neighborhood functions actually can be computed in two different ways. One way is that the buffer analysis specifically, so just create a radius of 2 kilometers around all the points, and then the corresponding area will be giving you the actual neighborhood functions or the service areas. But that may not be an appropriate one in all the cases, specifically in the cities, or in very undulating areas where the connectivity of roads is actually a major important factor to determine what exactly is the distances or surface area of any points. So in such cases, the neighborhood functions can be computed based on the distance. So if you want to compute these neighborhood functions, again, I'm trying to emphasize over here is that to make a distance-based, cost-based neighborhood analysis, your data set should have a topology built in. And those topological, after building the topologies of the data set as a single integrated group, it needs to be converted back into the network data sets, and then the analysis can be carried out. So any neighborhood analysis specifically other than the radial distance based approach. The topology building is one of the important criteria. And uh, and these distances, apart from the distances, there can be any other criteria which can be linked in, like we want to find out how many people are living in a particular area around a point, or it may be what is exactly the actual average household income. That can also give an idea of what may be the expected income of those physical shops, or shops and the corresponding investment the people needs to make in, and so on. Is the neighborhood area is actually located in high risk zone, and so on. So accordingly, there are different type of proximity functions which are the requirements which can be fulfilled with different neighborhood functions. So it's basically a category is either it may be a buffer or vector based approach, which are actually geometrical distances. There are other proximity functions that is called Artesian polygons, and this polygons actually has been used and earlier also, like the JAS. One of the famous JAS analysis is actually which is being used in medical science to find out uh, the cholera, how the cholera is actually getting affected with the water source. So water source is actually an important component of spreading of a cholera. So over there, the proximity and spatial analysis actually related to, and then the usage of Thesian polygon actually helped into support that argument, and later on it was found to be true. Similarly, in case of raster neighborhood function says we need to have an spread flow computation, which means that if you're having an TEM or slope map of a particular area in a raster format, now we have to find out what may be the catchment area, or what may be the area where the water is getting collected. So for that, the flow models or flow accumulation algorithms is actually is getting computed under the uh, spread computations techniques. There's also an seek computation, which also which talks about that if any service is being, or if any activity is being triggered at one grid of a raster, so which will be the first point which will get affected. Those are actually the seek computation point, which plays an important role. So we'll see one by one those cases. This is actually a buffer analysis of a single layer, or there may be a multiple layers. So it's like we can have a uniform buffer across all the lines, or we can also have a buffer of different lines. So these are actually important in the cases like there may be a road networks which is being considered as a highway or the national roads, and there may be sub lanes or the street, especially in the city streets, can also be there. So those different conditions can be created in a buffer zones. And in the buffer zone, the neighborhood again can have a multi-layer buffer analysis. So within the different zones, which we can have different neighborhood associated with that. And again, each of those again can be one of the criteria to give you the outcome of the neighborhood functions. So grouping the different raster operations in a group, generally those raster operations can also be then local operation which is being performed on cell by cell basis. Means like what you're doing is you're carrying out the activity on each and every cell. For example, if you want to carry out for integration of different conditions, like condition one is fulfilled and second condition is fulfilled and third condition is fulfilled, then in those cases each of those suitable grids will be working in tandem with neighboring layers, but the grid numbers will be the same. In that case, the operations will actually be a local type. In case of neighborhood operations, basically it considers the radius of impact each of those operations. Let's in the cases like this is also called a kernel-based approach can be used. There are also a few filtering and cleaning of those data set is also possible. The way we are using median mod filters, so that can also be used. So those are actually a few functions which is actually a neighborhood-based operators. Then there are also a zone specific. So a zone specific is actually different grid points, but belonging to the same class, and the operation has to be performed in those areas only. Like you may be having a raster map generated from a satellite imagery after doing a classifications. So in your study area, you may be finding out the multiple patches of forest area spread in different locations. So now there may be requirements to generate a buffer zone around them, to do ecological studies, or maybe to just to do create a corridors. So it's like there may be multiple requirements related to that. So depending upon the cases, the each of those forest actually and the forest patches will consider to be a part of a zone, and then inside that around that zone or inside that zones we are going to do a carry the activities or the operations, especially the analytical operation which will be carried out. So this gives the three different categories of those operations. And one important thing which you need to look for specifically in local operation is that if any data any grid which is not having any value associated with that, the output of all the process again will be no data only. So it will not be the output will also have no data associated with that. So I mean to say that even if you do for example, in case of reclassification, if any reclassification, if you're giving some conditions, so after the reclassification, all the cells which is having no values will be converted back into no value outputs. The neighborhood functions, the uses are very similar to the different raster based which is being used in image processing. But there is slight differences in the cases in a GIS where we have the specific functions. For example, we need to find out the focal sum. So these are actually required for the cases like flow accumulation. So you may be having a grid, each of those grid may be representing that what are the different grids connected to that particular grid. For example, on the left side of this raster data sets, we are having a one. So it means like it is having connectivity of ones where the water source can get into the systems. And then if you want to find out what will be the impact as a whole, if we if we is it that there will be a flow or accumulations in all the grids, or what is the total flow accumulations in a specific grid. In such cases, the focal sum is being used. So it's what happens is that a simple kernel of let's say in this case is 3 by 3 is being put on the focal operation, focal locations, and then summation of all the grid values which is being computed to generate a new output. So this way, the iterative approaches is being carried out to identify or do a segregation of is there any area where accumulation is happening, or is there any area which is where flow of water is in continuum, and so on. So that actually helps in segregating a watersheds in a different studies area. In the zonal operations, what happens is each of the cells need not have to have a contiguity or in a continuation. Like in case of focal operations, we are talking about the neighborhood. So it means like on any grid, the corresponding neighbors has to have around or the existence of the neighbors has to be around that particular grid. But in case of zonal operation, what happens is that those grids can be at different locations, but all of them has to be categorized in a single grid. So that is the differences between the focal operation and the zonal operations. And under the zonal operations, again, we can have different operations. For example, if you're having a land use classified maps, which talks about that you're having a different category of land use like forest, agriculture, and so on. And we want to find out what exactly is the forest area. So in this case, we need to count the number of grid or pixels with a label of forest. So that will group together, and then that can be shown. And like that can be computed, and the corresponding area can be computed as we have seen earlier, based on the each pixel size. There may be this. There may be other cases where multiple rasters can interact with each other. So that is also possible. Like two different data sets of same zones can interact and produce the new summarize and output. So that's how the zonal operation actually can be performed in the raster domains. There are other operations. For example, we need to have a zonal input. Based on that, we can have on the different classes and their corresponding statistical distribution, which can again help them to find out like land conversion rates, and different other applications are there in case of zonal analysis. So zonal histogram is one of them. So in nutshell, what we can say is that in local operation generally is being used in application like change detection studies, or it's also used to find out the favorable wildlife species. Basically, it's being used to generate a suitability map for different species. Then there's a process of simplifications, which again allows you to create groups or simplification of your data sets. So that is again based on the local operations. It's basically a summarization. So let's say we are having grid data sets at 3 kilometers. Now we want to generate the output and at 9 kilometers. So in such cases, we need to have an average values or mean values or maximum values, which is falling in a coarser scale. So that for that, a simplification has to be carried out. We are also having a reclassification or replacement value. So those are also can be considered to be a part of local operations. And in cases where we need to do focal operations are basically data simplifications like categorizations or terrain analysis, where we can say that which of those area which is visible, which of those areas not visible, or shadow range. The corresponding also the aspect of terrain can also be computed. In image processing, it's been widely used, especially the different kind of filters like statistical filter wherever we use it. So this is one of the applications of neighborhood operations. In case of site selection is also an area where the neighborhood operations can be used in. The zonal operations specifically being used in landscape ecological analysis, habitat analysis, and similar studies is required to have a zonal operation there. It also helps in doing a comparison of different data sets, as we have seen in the zonal histogram, which talks about how the distribution of different land use classes is there under the different groups. So that's how the different applications where we can use the local raster or raster-based analysis. Now I'll be talking about now is that those are actually the tools which is existing, I should say, around the last 10 to 15 years, and people are actually using those tools and techniques in GIS domains. Now I'll just talk about the recent development where the GIS is actually moving in. So in case of GIS, one of the areas where advancement is happening is actually a 3D analysis. So let's see that how actually the 3D analysis requirement has come in. So earlier, if somebody wants to view terrain variations in a map, so the hillside method was one of the ways. So the people will have to have a paper-based map, and where different tones or different shades of a color or tables can be used to differentiate where exactly is the height variation, or which are the area which is having at higher location and which are the area which is at lower location. So it's just a 2D representation, but the use of the color variables helps a persons to visualize what exactly or how does the profile of a terrain is varying. Later on, people have started using the data sets of the grid, and they just try to extend it in a perspective views or 3D coordinate perspective view representation. So that's what we call it as a 2.5Ds. So in that case, what is happening is that on each of the grid places, we are having values that gets extended based on uh, the the values on those grid data sets, and those values can be considered as a height in a z direction. So location x and y is being fixed, but attribute is being taken on the z directions, and that's how the visualization of 2.5D terrain method started. This is actually a relative data sets where the disparity of terrain is being created, and then correspondingly the generations can be carried out. Later on, the people have started creating an NLGIF stereo images. So it's actually generating the same terrain, but taking the images from the two different perspectives. And those perspectives are being created in such a way that the base by height ratio, or the distances between two exposure station and the height of the terrain, that ratio is remain more or less same. So that's actually the condition is being applied to get a better result. So that gives the kind of, so if anyone who brings out his and like the blue and green specs, where or any specs which is having two different colors can see this terrain and can feel the variation of terrain in these images. So in this case, actually, the perspective, or I should say the extrusion of each of those terrain area is actually based on the how exactly it looks like, but scaled to the data processing scaling system. So based on that, we can, but the user can feel wow, how does the different portion of the terrain is changing. So that those were actually the cases where the raster data set has evolved earlier in case of 3D GIS analysis. Similarly, there has been an attempts to create different vector data sets and the corresponding attributes visualization. So each of those vector data sets gets extruded and the corresponding visualization started coming into GIS domain. So it's like the way we create a 3D raster or 3D bar graph in different with the different data sets. Similarly, each of those polygons used to get extruded and corresponding values can be represented. But people have later on, there's the way we are having starting, especially the lidar based data set, which gives the digital surface models. So based on that lidar data sets, we can have a DSM visualizations, and that the softwares are now allowing it to be viewed in GIS domain. Nowadays, what is happening is that the 3D GIS data sets, whenever we say, the earlier it was only restricted to the visualization of the data set, but now in the 3D GIS, actually it's going in a different applications. The 3D GIS has now applications in architecture, environmental modeling, archaeological studies, also have in urban planning, geological analysis, the hydrological surveying specifically to find out subsurface terrain details and build a computation models to find out the suitable petroleum sites and so on. Navigation is the another area which gives you the location-based services, and it's widely available through Google Maps services. That's the one of the applications which we see. There's also an needs to have an and like there's also uses in underground water supply, again extension of civic body services. There's a marine biologies where the people are using 3D GIS to visualize and measure the different concentration of oxygen, lighting, and based on that, carrying out the biological or the conditions where any specific species are there. There are also uses of 3D GIS in modeling, especially the ecological studies, where it talks about that how the statistical data can be looked into and we can find out the species distributions in different areas, and based on that we can generate and do a simulations for different cases. So there are a variety of different applications, and it gives the challenges in a different domains also, starting from the computational requirements, improvement of algorithms to carry out and finding out the patterns, the area where the current application is going on. So let's see that example of simple virtual 3D city models and how it's being used in different cases. So let's say we are having an 3D models which is available to us, and there are different ways of generating it, those 3D city layers. So those can be generated in automated ways, there is a semi-automated ways, there's a manual methods. So there are different ways of generating those data sets. So somebody has, let's assume that somebody has generated those data sets, and those data sets are actually made available to us. Now, if those data sets are there, then that can be used for a landscape visualization. So if from the planning point of view, if you want to see if a few of the condition is being taken in how the city will look like after the transformation or expected transformations. So that's one way of doing a landscape visualizations. We can use these 3D models to do disaster management, specifically to find out what are the inundations areas. Now we are seeing that there are a lot of requirements are coming in, specifically if we see the city-specific flooding, which we are seeing nowadays, which is happening in different cities. So accordingly, we need to find out which are the areas which are prone to have flood problems, which are the area, and what may be the reason for that, if any failures happen. So such kind of cause an impact analysis, and correspondingly, especially in the flood simulation management, which we can use it. There's also ways to find out the different change detection in 3D spaces. So if any area is getting converted into a new area, or redevelopment happens in a specific zones, so we can identify what exactly what are the areas and how much changes has happened in those locations. This helps in a different ways, like for example, if one area was having a one-floor building, now later on there has been a redevelopment plan, and that particular area got converted into a 3-floor buildings. So accordingly, the civic bodies has right to have an additional revenue source for those extra 2 floors. So people can identify and then and then based on that, the revenue generation models can be created, and the monitoring can be carried out. Now, there is also a need specifically for setting up new business opportunities, especially now it is also getting integrated into in business intelligence software systems, where the data sets gets created in 3D 3D forms, and based on that we can find out what exactly is the area which is having an economical cost, or the activity which is going on. Then again, there may be cases like a small area, but due to the multi-story rise of that particular area, the catchment or the per capita revenue, or the revenue per unit area will increase. So such kind of, based on the data sets, 3D data sets, we can do an economical modeling, or to find out those potential areas. There's also a cases, for example, if somebody wants to set up a solar potential application is the another area. So if we're having an layered out different building plans. So based on that, we can do a computations, especially based on the view shadow analysis and the availability of uh, sun on a particular building, or the surface area which is getting exposed. So based on those, we can do a simulation and provide an expected energy efficiency of uh, each those buildings. So in such case, we see that the different virtual 3D models has a variety of applications, and just a few of them. There are multiple other applications are also there, where the 3D GIS is getting integrated with the modelings and gives a very good results for solving different real-time applied science problems. There also we are having a special queries in GIS and raster base, especially the planimetric queries. We are also having now the query which is possible to carry out in the 3D domains. So like we can select, we can find out the different attribute of a building. We can also do a spatial distribution based on the height of a building. So that gives an idea of how actually city is growing, and that also gives an idea of why city is growing in those lines. Like we generally will see that the lower level of floors will be available at the periphery of any city, and the higher rise buildings will be at the core of those cities. So this helps us to identify what are the core areas, and correspondingly the different distribution of those buildings can give a lot of variety of other informations. There are also a base of filtering. So instead of having one particular building and getting the output, so the way we use the spatial query where we select one polygon and get the details. Similarly, we can also in case of 3 data queries, we can give the criteria, and based on that we can see the highlighted locations. So that actually will help us to do segregations of the different distributions and try to understand why exactly that segregation is there. People are also now doing simulations to combine the geospatial domain with other simulation and modeling flow approach to do a temporal animations. Like this is the example where it shows the dam breach if it happens. So at what particular time, what will happen to different areas, and how much water will be available in different locations that can be tracked in. So again, this has an applications in disaster management services. So in such kind of applications, generally requires to have a workflow. So those workflow are actually is being generated. There are a lot of different approaches are there. So one of them is that you do a data collections, 3 data collections, and create different height maps. And those height maps are actually get integrated with your different 3D footprints of those maps. And based on that, we create 3D base layers. So this gives you a lot of opportunities in a different domains, like automations for conversion from radar points to building height extractions, taking context into consideration and improving the accuracy of those buildings. Then there's also possibility to create a different generalization approach, which exactly will match to the ground realities in case of automations and so on. Then also the matching and pattern identifications, taking context, the neighboring context into a point, and then generating the actual base layers. So once the base layer, once the base layer gets generated, that can also be integrated with existing layout plans of other areas, and combining them together, so we can carry out a simple visualizations of the area, or we can also do a carry out the analysis which we have worked out, like solar potential and other things. So this just shows the steps in a nutshell. What we need to do is to create a complete 3D GIS data sets. So the way we are having the interactive visualization, same way we're also having visualization in 2D domain. We also have a 3D domain interactive visualizations. We are also having an 3D based queries like the buffer analysis, which can be carried out. So if you want to find out what is the impact sphere and inside the sphere, what are the different buildings which will get affected. So this has again multiple applications specifically in finding out the explosion impact. Then there are also cases where the resistance of a specific building can be used, and then accordingly the risk assessment can be carried out for different zones. There are also an opportunities to find out like the height, area, and volumes of a building, which helps us to do an estimations of overall cost of any decisions. Let's say if as a administrator or maybe a owner of a particular building, we need to just do an estimation that what may be the cost if we repaint the whole wall. So in that cases, we need to have an area estimated, and based on that, again, we can do a cost estimation. Same way, there's an area estimation, a volume estimation per capita requirement is there. So such kind of requirements can be fulfilled using 3D spatial analysis and queries. There are other analysis in 3D domain is being done like to find out what are the area which is actually is within the range, or what are the area which is not visible from a specific point. Again, this helps in to do a placement of different cameras, and then based on that we can do a proper optimization of placement of the cameras can be done it. So those analysis can be either in a 3D domain, or it can also be in a ground coverage range also we can do it. Similarly, the terrain analysis or the rainflow analysis, which talks about that what are the area which is actually rain shadowed areas. So accordingly, that can be used to do an estimations or planning for different water resources can be used. There's an also for the cases where we need to identify the solar potential of each of those building, and we need to have a latitude and longitude known for that building, and that actually will give the estimation that each of the day what is the actual total solar energy available and at a specific time, and that can also help us to determine the impact of high-rise building on the neighboring buildings too, and the corresponding that can be taken into computation of solar potentials. This is just a few examples where the pattern-based approach is being combined together with 3D visualizations, and based on that the simulation and planning can be done. So this is just taken scenarios that with the in locations we have identified, and the corresponding growth rate has been identified in a specific locality of a city, and there are also a few conditions which needs to be considered. For example, in India we are having a restriction that within a 200 meters of any ASI structures we cannot have buildings more than 15 meters. So if that comes same way, we can have a multiple landmark requirements which can be put in to do a simulation of a specific building and look for expected projected growth in third dimensions. So building height area is being taken. So this is just an input where the few last year trends is being shown that what exactly is happening in one locations, and then after what is the expectation that those area will get developed, and what may be the impact in landscape of a city area. So that's how the pattern identification, when it gets integrated with the geospatial domains, we can solve or we can try to do a simulation for the future scenarios, which are actually helpful for doing different kind of planning, maybe city-based planning or regional planning, and so on. Along with that, it has also have a different potential and in a business opportunities, identifications, the catchment area, placement of the new uh, banks, ATMs, that there's those kind of requirements can also be fulfilled with upcoming 3D GIS analysis, because 2D GIS analysis is not going to help much due to the in a satellite image or anywhere we'll only see the spread in 2 dimension, not getting a spreading across. But nowadays we are having a vertical expansion, and that needs to be taken into an any kind of modeling approach. So that's how the different residential and planning area can be carried out. That was the cases where we say that this is the cases where at one time what was the case, and if we go away and if we continue with the status quo, then probably we'll see a development specific areas. There may be cases as a planner you would like to evaluate the different planning schemes. So that was the one scenario where we don't do any changes as a planner, or there may be cases that we want like to have a relocations or the reconstruction. So this is how, if we go for another scenarios where we'll accommodate it in particular areas, and based on that we can go for an high-rise building, what may be the expected uh, input or requirements to accommodate the additional demand of populations, and as well as ensuring the total open areas of a localities. So different scenarios can be simulated, and that can also give an idea to a planner or decision makers to go to take and decisions and uh, expected cost in making changes on the ground. So these are actually the few of the applications in our centers which we are carrying out. There are also other applications, or the applications are there. People are working on that, so you can visit our website. And we're also having a YouTube channel, so where we are also having additional courses related to the geospatial analysis. We are also having an e-learning portal. So please do visit at irs.gov.in for more details. Thank you.